We are lucky to have here with us Mark Redding, President and co-founder of Poseidon Systems. Mr. Redding has more than 30 years' experience in developing and deploying condition monitoring systems across multiple application space. He was formerly founder and president of Impact Technologies, a company focused on developing condition-based maintenance and prognostics and health management solutions for the US military, including vibration-based and fluid diagnostic systems. When Impact Technologies was acquired by Sikorsky's aircraft in 2011, Mr. Redding retained ownership of the fluid diagnostic business, which today is Poseidon Systems. Poseidon offers a range of oil sensor and a cloud-based monitoring platform with more than 10,000 installations in the wind energy, mining, marine, and rail industry. Thank you, Mr. Redding, for coming here.
Do I need this? Oh, yeah. Okay. Thank you. Let me first apologize that this is going to be in English. If I tried it in Spanish, you'd have a harder time understanding me than you'd have being able to understand my English. So this presentation, I'm going to give a brief introduction to our company. We're based in the US. Why there's a need for condition monitoring, continuous monitoring for machinery health management, limitations of offline oil analysis, which is predominant current practice, and then a discussion about metallic wear debris monitoring, what it is, how it can be used to help manage equipment problems. And then I'm going to present some information as to why some long-held beliefs about wear generation, at least as it applies to wind turbine gearboxes, why those beliefs are flawed, and present a few case studies demonstrating benefits of online sensors as being suitable for replacement of periodic oil sampling. Okay. Our company, again, we're US based outside of Rochester, New York. We specialize in developing online oil sensors, although we also incorporate other technologies as part of a holistic condition monitoring system. We have, much like was presented earlier, we have sensors connected to an edge device and for cloud-based computing. In terms of our existing footprint, we have installations in over 10,000 large gearboxes, 700 Zenith thrusters in a marine application, 300 diesel and natural gas engine installations, and in terms of markets, an expanding presence in oil and gas, oil refineries, natural gas compression stations, fracking pumps. ExxonMobil recently selected us as their technology partner for a new platform that they're introducing called Mobile Serve Asset Management. In power generation, wind turbines is our biggest installed base, gas turbines and steam turbine monitoring, and probably our second biggest market is in the mining industry, monitoring diesel engines on haul trucks, loaders, shovels, and also fixed plant equipment. So much like is common, we have sensors connected to an edge device, and then ultimately connected to the cloud, either through Wi-Fi, cellular, or a wired connection. And then we have a platform called Poseidon Live for doing the continuous monitoring. What I'm going to, let's see, this isn't pointing. The two sensors on the left are what I'm going to focus on today. In the limited amount of time, I'm going to talk about the top one is the metallic wear debris sensor, and the bottom one is what we refer to as an oil quality sensor or oil condition sensor. Oops, okay. So this chart comes from reliabilityweb.com, and they're showing a curve up top You might call it a traditional curve, how things fail. But then in the fine print, they say that random failures account for between 77 and 92% of all failures, which if you read that the other way around, only between 8 and 23% follow that curve up top. So that's more of a wear out type. So to be able to detect these random failures, that's part of the argument for continuous monitoring. I'll give you an example that you can all relate to. The tires on your car, right? You would get so many miles on those tires. And the tread wear is going to be dependent on the road you drive on, your braking, but it's relatively predictable. You don't need to monitor your tread wear on a continuous basis to know when you need to change your tires. You would check for that. Another type of potential tire failure is through pressure loss, either a broken seal on the rim, a puncture from a nail or a sharp metal object. And that's why many vehicles today have continuous tire pressure monitoring. That's something that can go pretty quickly from a small problem to a big problem. So in a similar way, the application may dictate whether or not you need continuous monitoring or periodic monitoring. So as it relates to oil and oil analysis, there are going to be some applications where periodic oil analysis is fine. But in situations where a failure or a problem can occur in between samples, you need something that's either sampled more frequently or continuous monitoring. Here's a similar curve, and as it relates to those two sensors I talked about, the oil condition monitor, go back, is in the proactive domain. By monitoring the oil, you can take action to, let's say, change the oil when the oil, say, is oxidized, additives depleted, overly contaminated, to prevent machinery failure. The other sensor, the wear debris sensor, a metallic wear debris sensor, which counts and sizes individual metal particles in the oil, is more indicative of the machinery health, not the oil health, but the machinery health. The two in combination, coupled with, let's say, vibration, other sensors can provide a more holistic picture of the machine health. So we talk about asset health management. Well, you can't manage something that you don't measure. I'll give you an example. So I was diagnosed as a type 2 diabetic a couple of years ago. And my doctor talked about managing my diabetes. Well, what the hell does that mean? I get a blood test once a year and get a reading on that day, on that hour, that I assume doesn't fluctuate that much. So I got a continuous glucose monitor. So I can check my blood sugar, instantly, all the time. Very first day. So ideally, your blood sugar is below 100 milligrams per deciliter. That's a non-diabetic. So my blood results said I was 120 consistently, well, multiple times. First day, I've got this. I go for dinner, and I'm trying to make healthy choices. They have the greasy hamburger or a bacon, lettuce, and tomato sandwich. I take the bacon, lettuce, tomato sandwich. An hour later, this thing's going beep, 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 beep. It was over 200. So what I never knew is that your blood sugar can fluctuate drastically throughout the day based on what you eat, what you drink, exercise. But absent of this device, trying to manage my diabetes would be difficult because I wouldn't know the direct impact of something that I eat on my blood sugar. So that's an example of having the right tool for the right situation. So the frequency of measurement needs to be often enough for the problem detection to provide for corrective action and to prevent catastrophic failure. I'll give a couple examples. So here's an example of why online oil monitoring. And over here, there's a couple of charts that show a typical situation where an oil sample is taken, and the line is showing the overall oil condition degrading over time. The sample gets shipped, the results come back. In this scenario, an issue begins on day 10. The oil sample comes, now this is unrealistically long, but 2 weeks later, the results of the oil analysis come back, so sample's good. Meanwhile, a problem has occurred. Same situation with continuous monitoring. Issue begins, issues detected, issues investigated and repaired, and things are back to normal. So with online oil monitoring, it's always on, allowing for detection of faults earlier. It enables proactive maintenance by catching conditions before they cause damage. You get repeatably consistent data, whereas with oil samples, depending on who's taking the sample, where they're sampling, when they're sampling, where the sample's going, the data sets are much less repeatable, consistent. Safety is becoming a bigger thing. On the assets that we're on, many of them, they're large pieces of machinery, mining trucks. Anytime a human has to touch the machine, there's a chance for an injury. Many times these things are in remote locations, especially, let's say, in the US where things are more spread out. Natural gas compression stations generally are in remote locations, and taking oil samples, a technician may travel to site just to take an oil sample because they need to take it every so many hours. So eliminating that periodic sampling would reduce the cost of sending a technician to a remote location. And the reduced dependency on lab analysis allows for oil sampling to be taken only upon exception. So, and again, this is going to be application specific or dependent, but in wind turbine gearbox application, the typical trend is to take a sample once or twice a year. And in these samples that ExxonMobil processed, 99% of all samples came back as good. The 1% that were bad, samples were retaken, and 50% of the time, those were good. So those numbers tell you that the sampling is unnecessary. It's unnecessary to sample that many times. What you'd like to do is only take that sample at 1% of the time because a sensor told you there was something wrong. So some of the limitations of offline oil analysis are sampling frequency. Again, it's only practical. I mentioned wind. The trend now is to sample once a year. Other equipment like rail locomotives might be once a week. If a problem can go from first detection to failure in less than that 1 week interval, then that sampling frequency isn't fast enough. Sample size can be another limitation. So the small samples typically taken in an oil for an oil analysis many times aren't representative of an entire sum. Sample variability, I mentioned whoever's taking the sample, you can get different results. And then sending samples to different labs can result in different results. A quote here from Mark Twain: "To a carpenter whose only tool is a hammer, everything looks like a nail." Point being, if your only tool available to you is an offline oil analysis, you're going to use that in instances where it may not apply. Okay, this is the oil quality sensor I mentioned. It operates on a principle of electrochemical impedance spectroscopy. Basically, we're looking at electrical properties in the oil at different frequencies to infer things about the oil. The output is basically data points on this curve. I won't get into too many of the specifics here because I'm running out of time. Here's an example on a natural gas engine. The blue lines are the sensor output. The orange line, the circles are dots from the oil sample. The left-hand axis is one of our output parameters, referred to as bulk resistance. In this case, we're plotting bulk resistance against the lab IPH, and you can see the correlation there. Similarly, high-frequency bulk impedance. And again, these discontinuities are when an oil change was performed. And here's versus TAN and TBN. Now, this bulk resistance parameter is inversely correlated to TAN, but you can kind of visually see how they're correlated. So that was demonstrating the ability for the sensor to track and report on parameters that would come out of an oil analysis while not directly measuring those parameters. And let me quickly get to the metallic debris sensor. The analog signal, this is what one particle looks like traveling through the sensor. This is a wind turbine gearbox. The different colors are total counts observed of certain particle size. Excuse me, here's this is a table of the counts in those different bin sizes. You see a histogram. What I'm tending to show here is when this gear tooth fracture occurred, there was a large burst of metal with really no warning ahead of time. Using periodic sampling wouldn't have identified that. That signature looks drastically different from a bearing spall. And here's an example where we detected low oil. We saw a large number of small particles, notified the customer, and once the oil level was restored to the proper level, the wear generation stopped. Actually, in terms of problems with equipment, the single biggest problem isn't good oil or bad oil, it's oil or no oil. And I think my time is about up. I apologize, I didn't get a chance to cover all my slides here, but they'll be in the presentation that you'll all be able to receive. Thank you.
Thank you, Mark.
Okay.
It's a pleasure to have you here. So, who is the brave that is going to ask a question? Yep, Antonio.
This is Antonio from Enel Green Power. So regarding your particle counter sensors,
Yes.
is calibration needed?
Is
Calibration needed? No.
Calibration.
So you need a pre-calibration before installing the sensor in the wind turbine?
No
It's not
calibration
It's
needed,
not
no.
required. Okay. Thank you.
Sensors are all calibrated at our factory.
Thank you.
Sorry. How many kind of sensors do you have, or for which proposal? As I see, you can measure non-magnetic and magnetic particles, but how many type of sensors do you have?
How many types of sensors?
Yeah.
For
example, are dedicated only for machinery or for mechanical part, like rotating turbos, or are also dedicated for electrical components like trafos? For example, if we want to measure DGA, we can measure?
No, so that's, we don't offer a DGA sensor, but
Okay.
the oil quality sensor can measure the properties in the transform oil itself, as opposed to measuring the gases in the headspace.
Okay, and we can difference this kind of elements,
Yes.
like nitrogen, oxygen?
No,
Okay.
but it's sensitive to the degradation of the transformer oil.
Okay.
So, thank you.
So, last question. Thanks, Mark, for the presentation. Only one misunderstanding from my side. Is it possible to detect contamination and water ingress or water percentage in the oil with the same sensor?
Yes. Well, with the oil condition sensor?
Yes.
Yes. In fact, I had to jump through it. We have a direct measurement of water in that sensor.
So thank you, Mark.
Thank you.